Hey everybody, it's Obi-Wan Pez for nSimplex Pachinko. We are starting class a little bit late, sorry. Had some stuff going on at home, so just gonna get into that. If anyone is planning on joining the differential equations class and being a part of the on-stage crew over here, feel free to join the Discord, join the event stage, and if you are a known member of the community, we'll invite you to speak. If you're not comfortable with that, that's perfectly fine. You can contribute and participate from exactly where you are. Stooky! Thank you very much. All right, we are going to delay this ad break for 15 minutes and just shove it way off to the side. It's fine. We'll do a 1-minute break later. Alrighty, so we're going to unmute here and get into our class. So, good evening.
Hello. Good evening.
And if the stage crew would like to introduce themselves one more time, we'll get on with class.
Excellent. I'm enstucky. I do math over at enstucky, and I just rated in. So,
Thank you, Zach.
Yeah, I'm Zach. I stream over at e2iPi, and I've been enjoying this differential equations discussion we have twice a week. It's been fun.
Alrighty, and thank you both for coming. It's always a treat to be able to have, further discussions than, necessarily that I have been having with my students, which tends to be rather one-sided. Because we have, goals and stuff, and schedule to keep.
yeah. That is the way.
So it is one of my favorite aspects of both this class and real analysis that Zach ran in the winter/early spring, which was that, we just can talk about whatever comes up, and if it takes 2 sessions, it takes 2 sessions. Overall, generally, this format has been going much faster than a typical class, but I would argue that's probably because of our level of familiarity, but
Yeah.
might have something to do with it.
Maybe.
Alrighty, so why did that just happen? Okay, whatever, it's fine.
Shift.
Yep, cool. Okay.
Mind popping a link in there for us?
Yeah, I suppose I could do that. Apologies.
Yeah, all good.
All right, and just to make sure I don't have that up, but that's fine. It is on a different window. Okay, that's for later. Okay. So last class, what did we talk about?
mean, I remember we talked about exact equations.
Okay. And exact equations were what?
Did we lose Suki?
Uh-oh.
I think we. Oh, Suki's coming back. Okay. So those are ones where we had you could find a potential function. I believe is what we said, is that you could find, they were of the form, we had partials, right? The partial derivative of dx, partial derivative of dy equals 0. And you're able to show that the mixed partials of your function are the same. So your mxy and nxy, as far as partials with respect to x and y, are, I guess, psi, if we're going to use that notation, are equal.
Right, so we had this.
To a constant. Yep.
You said mixed partials?
Right. So I guess you could take, if you made the presumption that you had a psi xy, like if you had an mx and an ny, you could take mxy and nxy, and those are equal. Sort of the assumption we make.
Right, so what we're going to generally see is, as Zach said, m of xy times dx plus n of xy times dy equals 0. And, oh, sorry, Stuki. Seem to be having some audio issues. Sorry. Just shift. Stuki, I don't know if it might be worthwhile to restart your computer, but otherwise, you know, feel free to still jump into Excalibur. So let's see, Zach, you said C is going to be so-called potential function.
Hmm?
And again, we saw that as this combination of functions such that, right, our gotcha. Such that m, when we take the partial derivative with respect to y, we may have had this the other way around earlier, and apologies for switching all the time, I'm sure. Such that in this particular case, if we take the other partial derivative than the one that was already taken, so in this case we have m dx. If we take dy, partial derivative with respect to y, of m as it's there, then we should get, if it's exact, the exact same thing as when we take the partial derivative with respect to x of n, which already had a partial derivative of dy. So ideally, this is what we're going to have. So if you have an exact equation, that's what we're going to see. And we can check with whatever function we have by, again, taking the partial derivative that's not already there, and that'll show up that'll bear out in this particular case. Either we do, and that's awesome, because it's fairly easy to work out then what psi is going to be, this function over here. And if not, what happens?
So if it's not some C, you mean?
If it is not an exact equation. Yep.
Then it's just a differential. I mean, I don't know. If it's not exact, we can't really find this potential function.
So ideally, we do have another method to be able to figure out how to force the differential equation that we have to become exact.
Right. So is that where you wanted to go with this? Is the like a transformation of sorts?
Yep.
So what you can do is you can take the you can make a substitution. See, I've forgotten this substitution. I know it has to do with
Yeah, it was after you left.
it was after I left. Yeah, I was gonna say it's been a hot second since I've done this. Normally, when I have most things that I encounter, like, to be honest, I don't encounter exact equations in practice all that often.
Mm-hmm.
Like they exist, but the transformation eludes me. I know I know you can. It's just I don't know how.
Yep. All right, so what we're going to do is we're going to take the original differential equation as it was, and we're going to say if we were to multiply all terms by some other function mu.
Mm-hmm. Oh. Yeah. Right.
Then we can multiply mu all the way across and find that there is a function that we can multiply across. We talked about this. Okay, we just got ads popping up. Nuts.
That happens.
Yeah.
Am I audible?
Yes.
You are audible. Yes.
Cool. And so are you.
Woo.
So perhaps this will work out.
Very nice.
One of the downsides of not actually being on time. Oh.
And we're back.
Okay. Thank you for sticking around, everybody. Sorry about that. I didn't do our traditional 3 minutes ahead of the start of class, so we're going to have to deal with like once every 20 minutes or something like that. We'll figure it out. All right, so if we do not have an exact equation, we can make it an exact equation by multiplying all individual terms by mu, which we have originally said, what if this is a function of both x and y? And originally, we had done, Stucky and I had worked out what happens if we leave it just as a function of both x and y. Stucky, do you remember, or can you relay, I guess, to Zach and everybody what the issue is?
It's gross. It's a partial differential equation. And
Say no more, Stucky. I get it.
all right, we're convinced.
Gross. That's all you had to say. No, go ahead and say it. I'm sorry. I just had to be.
No, I'm not sure. I'm not sure what else I was planning on saying. So when I say it becomes a PDE to solve for mu, to figure out what we would need to plug in there.
Yep.
And it's not exact.
I think Femvox offered a suggestion in the chat, and I'm trying to think that through.
Yes.
And I think that suggestion might work out.
Mm-hmm.
My partial m with respect to y, partial n with respect to x, subtract those and divide by n. And that, yeah, there you go. Yeah, I get what you're saying.
We gotcha. Yep.
Okay.
So the basic thrust is that what we're going to do is we're going to let mu instead be a function of x alone, or let mu be a function of y alone. Choose one, whichever one's going to be most convenient for your particular situation. So whichever one's going to produce an integral that is easily done. It doesn't necessarily have to be both of them. Stuckey and I were looking at one from last class. It was very ugly in y, but it was, or no, other way around. It was very ugly in x because it also had y in it. So that immediately brought us to the idea that, well, this was supposed to be a function of one variable only. So if we have two variables in there, it's just right out. Just throw it. And as a function in y, it was actually very easy. So it was like just dy over y, I think. Just cleaned up very, very nicely. So we let mu be either a function of x or a function of y, and then that's what's going to get us our mu is going to be equal to, this is e to the integral. And some people might be like, oh no. But that's actually okay. As a function of, and this is, I dare say this is probably backwards from how we had it yesterday, or 2 days ago. It's fine. We can do this by hand. Let's see, 3 exact equations and general. E to the m sub y minus n sub x divided by n dx, and mu of y is going to be e to the integral of n sub x minus m sub y over m, and that's in dy. Okay. And once we multiply this through, get it to all these individual terms, yes, I kindly let Stuckey work on the ugly part. Very true. Once we multiply through by either one of these functions, the new differential equation with mu becomes exact. So we are going to have an exact equation. It's going to be very nice. It's going to clean up, and we're going to get our psi very simply. So we go through and we take the other integral. So up here it would be the integral of mu m dx, and the integral of mu n dy should be identical to each other. And as we said before in last class, we do end up with, when we're taking the integral of mu m dx, we're then going to have a constant function with respect to x, so therefore it's going to be a function of y alone. And similarly, the other way for mu n dy, we're going to have a function of x alone, which is a constant function in terms of y. And then we just have to set those things equal to each other. Okay. So, today is 7/17. we're going to come over here. And seeing this in action, how do we go about solving the following differential equation? Ty prime plus parentheses t plus 1 times y is equal to 2t e to the negative t.
Well, we could make it look exact. Put it in the favorite form.
Alrighty.
Okay. Sorry. All right. If we multiply both sides by dt, we get ty or tdy undo plus t plus 1 y dt is equal to this, or plus we ty plus y plus or minus t is equal to 0. And check for exactness.
Brandon, we're going to do class today and not generally talk about politics.
Okay. Be careful here. So this is M, right? No, that's not true. That's N. M. So M sub y is equal to t plus 1. And n sub t is equal to 1. So not exact, not a big surprise, but then we're going to be looking at equal to, other way. E first, then an integral. Our numerator is going to be n minus m, or those things. So that's negative t. And I can divide by either n or m, so I'm going to choose n. That's going to be with respect to t, which looks like, and let me just make sure that I got those signs correct. No, if I divide by n, I need to do m minus n, which is going to be positive t. Okay, and so that's just e to the t.
I do have one small thing that I probably should have brought up earlier. It doesn't actually affect anything here, but up top is e to the negative t.
Mm. Sure
Like I
is.
said, it doesn't actually affect anything in mu, so that's good at least. But this is going to make things a lot simpler in about 2 seconds.
I'm very confused by what's happening on my screen
You have
right
drawn
now.
a line, apparently.
I have drawn a line.
Did you go off the screen
rid of
for
that.
some reason?
Whoa, I have no idea what's happening right now.
It drew a curve.
I'm gonna rejoin.
That's fun.
Come back. Alright, I'm back. Some minus signs in here. Maybe at the correct width. Okay, yeah, so the derivatives don't change. The mu doesn't change, but now we're going to scroll back to our so we're going to multiply this through everything. So we'll get t e to the t ty plus t e to the t y plus y minus 2t. Nice. 0.
Okay, and one more small thing. Your
okay.
y.
Oh yeah, needs an extra.
Alrighty. Thank you, Don.
Okay.
And Zach, if you wouldn't mind classifying the original differential equation.
Let's see here. So we've got
while Stuki's doing this.
Yeah, you're fine. Well, it's inhomogeneous. It's linear. Because we have everything in t. Notice that the fact that if we'd had y's anywhere, then we'd y squared or an extra y prime or something like that. That would make this nonlinear, but this is definitely linear. First order. An ordinary. Very ordinary.
Ouch.
This is ordinary. Yeah, whatever. Like easy. No, just kidding. This is so interestingly, the way of doing it is not the way I would do it. But I think this is a different way, and I sort of like seeing it this way.
Yeah, so this is laying the groundwork for what exactly you're thinking, I'm sure.
Where are we? M prime? What's M prime? M prime, where are you?
Right, so M, yep. There we go.
That's M prime. Okay, I see what you're doing now.
Yep.
I got you.
Not the
I
calculus
was thinking
prime.
of a derivative.
Yep.
Okay, that's not the same thing.
I got you, Stuki.
I think I'm being overly concerned before I finish calculating. So, and then M is gonna be okay. So some of this is easy. Let's just do that first. And then sorry, yeah.
No, I'm thinking about factoring out the y term perhaps that's useful. Maybe not.
Sure.
Right, given that it was constant with respect to t, that's an easy one.
Yeah. Because the integral of t to the t, that is that's a by parts integral, isn't it? So you could do t e to the t minus t, is what that would be.
T e to
With
t.
a constant on it.
Okay. How do I feel about that? I like that. Why? Cool. So these things are supposed to be equal. So the good news is that that term is that term. Oh, and then we get some nice cancellation. Wait, hold on.
That doesn't cancel, I don't think.
I think that t should be an e to the t. I think they should cancel. But I also think that's actually how the integral works.
Right.
Okay, and so
There we go. The yet cancels.
So, we've got the common term. And then C is going to be that. And D is nothing. So, that's nice. Or minus t squared. Okay. And so I guess we could write that as a function if we wanted, but
Yep.
we've never.
So, Zach, what was your preference?
So, first of all, this is sort of I think this is an interesting method. I've never seen it done this particular way. I've seen the exact equations, but I've not seen this like formulation using it this way.
Mm-hmm.
The way I would have done it is to take the whole the differential equation and divide everything by t.
Okay.
And the reason for that is because I noticed that there are some every factor had at least a t somewhere. That t plus 1 is a little awkward, but that's really my only complaint. But I think I can get around that better.
Okay. So I copy down the stuff at the very, very bottom.
And so really you could use the same method that Stuki just did.
Mm-hmm.
The convenience here is that now if I take the partial with respect to, for this n, our function is 1. Is this one m? Is that one on the left? That's n, right?
Usually.
Yeah, so that the first function here that would be a 1, when I take the partial derivative, that's going to be 0 no matter what, which is convenient. And then the end term is going to be 1 plus 1 over t. But then you can take derivatives as needed. So what's the...
I guess in this particular case, m sub x would have been 0, and n sub y would have been 1 plus 1 over t.
And that conveniently is something we can now integrate, right? If we can divide that, divide the 1, so we do ny minus mx, and divide by n or as desired. I would choose m equals 1.
Not mx.
Personally.
Yes, let's not divide by that nastiness.
I'd rather not divide by by n. That's my preference, but you know, xt, potato, tomato. I mean, of course, actual education.
Minus 0.
Yeah, minus 0.
And that was dt.
Mm-hmm.
Yeah, so e to the integral of, and in this particular case we get 1, well, it's just 1 plus 1 over t dt.
It's about to get very funky.
Yeah. A little bit. So we get now t plus natural log of t.
Which is really going to be t e to the t, which sort of mirrors what we had before.
Log of t, I see. Yeah.
Yeah, because you have an e to the t, and then you have an e to the natural log of t, which is just going to be t.
Sorry. Natural log e to the t and the int. There we go. Times t, parentheses around all that stuff. Okay, cool.
That's not exactly what I meant.
Nope, sorry.
No, I was gonna say that's e to the natural log of t, and then e to the t, separated.
Oh.
I mean, you could.
Yep. No, I got you.
I'm just using exponent rules.
Yeah, that makes it way easier. Right. So e to the t times. There we go. E to the natural log of t is just t. Okay. So this is our mu in this particular case. Keeping in mind, right, this new differential equation is ever so slightly different than the original one, but only in the sense that we divided by t first, and now we're saying that, oh, by the way, we're going to multiply by another t. So
right,
this is essentially just bringing that... Yep.
Yeah.
We're just essentially bringing the t back, but at the same time we got that e to the t. And yes, go ahead. Sorry.
No, that's sort of what we were noticing in the other method as well. That's all I was going to say.
Yep. And also, just as a matter of ease for the future, this is true. And Stuckey and I worked on this in general for any first-order linear differential equation. You don't have to go through all this rigmarole here that we did for this stuff. You could just take this differential equation here and say that mu is going to be e to the integral of this function. 1 plus 1 over t, provided that our y prime is has a 1 for a coefficient. So this is just going to be 1 plus 1 over t dt, and then we can do all this stuff to get back here again. Yeah, so this is generalized. For all first order linear differential equations. I guess ordinary differential equations, but at the same time, like, we don't have to worry about partial differential equations specifically. Right, so then this all just returns us back up to the top. The only thing that's ever so slightly different is that when you're doing first order linear differential equations, we're not doing things in terms of phi or psi. What we're going to be doing is saying once we get all this stuff multiplied out, we're going to be taking the left-hand side and assuming that it is a power rule. So our left-hand side ends up being d dt of, here we had y times t e to the t. Make sure that's right. Yeah, right. So we're taking our t e to the t, we're multiplying by everything over on the left, and then basically we're saying that our y prime is just the first part of the power rule, y, take its derivative with respect to t, and then we're multiplying by the rest of the stuff that's there, t e to the t. And then we're going to be taking the derivative of the not y stuff, so t e to the t, and then just leave y as it is. So once we get this all written out, this is going to be equal to the derivative with respect to t of y times t e to the t is equal to 2 times t. 2 times t. And then at this point we say, okay, we're going to take the integral both sides. This is going to be with respect to t. This uses the fundamental theorem of calculus. It says we get y t e to the t. It's going to be equal to, on the right, that's just going to be t squared. And then we divide off to get y by itself, t e to the t. And so y is going to be equal, it's plus c. Minus 1. Okay, so y is going to be equal to, that's going to be t times e to the negative t plus c times, I mean, it's fine. E to the negative t, and then all over t. However you want to write it, it's all the same stuff. All right. Comments, questions on that one? Yes, they definitely want formulas to memorize, and I have to disabuse them of that notion every time they come into a differential equations class. Okay. So since we've solved this analytically, this is what we get for our solution. Could we create a picture? Now, I left out, I suppose, a term here, but could we create a picture a priori, i.e. from the very beginning of this problem, that will tell us where various solutions will exist given some sort of initial condition, without having to go through all of the solution first?
Yeah, I'm guessing that link that you sent us is going to be that.
Oh, absolutely. So the first question, without giving away too much, I suppose, is how would we try and figure something out like that? Like, without having a calculator. How would Leibniz have done it back in the 1700s? 1600s. Man.
One more time, Obi. I just
Yep,
need.
that's
I
all
think
right.
I lost it.
So part B here, could we create a picture sort of a priori that would tell us where various solutions would exist given some sort of like initial conditions, given just the differential equation and not the solution itself yet?
Right. So, and I like what Fembox is saying here. You basically have y prime equals some function. Could you maybe talk about some stuff with that, right?
Sure. So if we start with 2t to the negative t. So if we start with this, how do we solve for y prime?
Let's see here. So you want to subtract your t plus 1 times y, divide it by t, and that would get you a y prime.
Mm-hmm.
Yep. So just algebraically solve that, and then you could figure out maybe if you had like a yt plane or something like that. So this is a function of two variables, so you could fit this in a plane. I think you could then talk about what the what am I trying to get at? What the y prime values are at each point.
Right?
And
So if
y
we
prime.
Go ahead.
Yeah, I was going to just add to that. Y prime is usually a symbolism of a slope in the derivative sense, and so you could maybe plot some lines, some little mini lines at each point.
Okay. So, right, too big. So what we'd be looking at is essentially drawing a whole bunch of what?
Lines.
What kind of lines? Going back to your Calc 1 stuff.
I was going to, well, slopes. I mean, actual education, Dr. Gold, slanty lines. I was going to say like lines. I don't know how lines are lines, right? Unless we're in like the sphere. You could say a line is a great circle. But
what geometric word could we use to describe them? Perhaps
that's smart Fembox, by the way.
Trigonometric.
I should do that more often. Segments. I mean, I thought of segments too. That's a good way to talk about it. Like little slopes. Little just giving an indication of what the tangency will be at that point. Are you wanting tangent?
Yeah.
Okay. I knew you were fishing for a word, and I couldn't think of what word you wanted.
So we're going to go for tangent line segments.
There. Okay. You're looking for an adjective. You could have played like Wheel of Fortune type thing.
Oh, I do that all the time where I'm on the front of the board and I'm like, come on, somebody say it.
Oh my gosh. Anyway.
So if we're going for tangent line segments for our y prime differential equation function, then what might some of the immediate properties jump out at us as? It's like, what are
for this example?
Yeah.
Yeah, okay.
For this particular example, right? What are some properties that are just like obvious?
Well, shenanigans happen at t equals 0.
Uh-huh. And in terms
you're
of
going to divide by 0.
In terms of tangent lines, those are going to be
the vertical.
Yeah.
Because you're dividing by 0, so your slope is infinite. What we mean by infinite is a vertical line.
Right. Some people might cringe
Slopes
at that, I'm
undefined.
sure, but you know what?
I'm speaking very loosey here, so.
Yep. Sounds good to me. What else?
Well, if you wanted the slope to be 0, then that would be where the numerator is 0. So anywhere that 2t e to the negative t over t plus 1 is where that let me say that again. That didn't come out right. So the curve y equals 2t to the t e minus t times e to the minus t over t minus 1. That curve is a slope 0, and I believe we call those nullclines. Isn't that the word? Because they have slope 0.
For us, that was
So
where a particular there was a particular constant value that was being used in the solution. So we said, like, if our c equals k, which Stuckey had back here, if k were 1, right, then the thing that makes up that particular shape is going to be a nullcline. And then if k equals 2, it's a different one, etc., etc.
That's right. Yeah, isocline. Thank you, Fembox. You saved me. Give the viewer a save.
Somewhere.
Do that. There we go.
There you go.
Have a save.
Woo. Right, so we could set it up.
That's the word.
We could set it up such that 2t e to the negative t is going to be equal to t plus 1 times y. We can then solve for y. We can do all sorts of other stuff and see what happens. I don't think that's going to be very convenient, so we'll let the computer do that one. Right, any others?
I'm trying to think what other things would be important here. Those are like the important ones, I think. You have things. So y only affects that second term. So anything the second term is only affected by y, but I don't know, like, graphically that we're going to see much with that. As t is large, good point. What happens? This first term's not going to mean much.
And t plus 1 over t. Yeah,
negative
t plus
y,
1 over t is going to be
exactly,
approximately 1, so we just get it's about negative y.
Yeah, so we're going to see a line. Or no, sorry, curve. That's going to be e to the minus t. You'll see like little exponential k curves.
Somewhat.
As t goes to t is really big. Somewhat.
Okay. So when t equals 0, that's going to be vertical. So we can just, okay. Draw in a bunch of vertical tangents that look more or less like this. I'm sorry, I should let you all do this. Okay, and we could, like, let Wolfram do the slope equals 0 part. Okay. This is a little weird, but at 0, it would also be horizontal. So this creates a little bit of a conflict. So our slope would be 0 at 0, 0, but also it would be infinite. So what does that mean?
The slope is 0. That would be where let's see here. That just means, let's see, this t is, so hold on. Basically, as we get larger t values, we're going to have slopes that are closer to minus y is. So on the horizontal axis, we're going to get a whole bunch of horizontal lines as t gets large, right? That's not exactly what you were asking. I know I'm like
True.
off topic here, but like,
That's
but
fine.
at 0, 0, yeah, that. I mean, I think we're gonna run into an existence problem, aren't we? I don't think so.
Yeah, so this creates a little bit of a problem. Just because our slope cannot both be infinite and 0. It can't both be vertical and horizontal. So at 0, 0 itself, because there's a conflict, there's another word that you all are probably learning in Penn's class, I believe.
Yeah.
Yep, Fembox has it. 0, 0 satisfies the initial differential equation no matter what the slope is. So we can't actually tell what the slope is at 0, 0 itself. So this is going to create a... well, it's more of a uniqueness problem than an existence problem, but...
Well, but the Picard theorem breaks. That's the point. Is basically we're not going to get. We can have. We'll get a 0 over 0, and in our y prime, and that's the real issue, is that that's undefined. So.
Right. So we can't have any of that. So we're just going to say like the point at 0, 0 is essentially going to be a singular point. It's...
Sorry.
Did a tab start talking without your permission? Okay. So we're essentially going to have this singular point here, which we're just not going to be able to figure out what the slope is at that point. We're just going to have to see what happens as we get close to it. If you want to individually study what exactly is going on with that, that's, from whatever direction, then that becomes more interesting. Our slope is going to be 0 along the curve that we set up there. So y was equal to 2t e to the negative t over t plus 1. That ended up creating a function that looks like this. It doesn't have a very high peak on it. It's only about 0.4. So, I mean, this is exaggerated a bit. But we're going to get something that looks more or less like this when we have a all horizontal tangents along that particular pattern. And then again, as we get really far out this way to the right, we're going to see that our slope is going to approximate y. So yeah, around 0, it's pretty close to 0. As we go up, it's going to become more and more negative. And when we flip underneath it to the lower side of this particular 0 function, then our slopes become positive. So even as it is, our y values are 0 over here, if we're on the opposite side of this particular function, then our slopes are still going to be positive. They're just decreasing ever more as we keep going further and further out. I'm exaggerating again, but it's fine. All right, and then as we get further and further in, there are a couple of kind of rules that we use. I'm not sure if there's got to be a theorem somewhere. It's basically going to be our intermediate value theorem, where over here we have a bunch of vertical tangents. Over here we have a bunch of tangents with very low positive slopes. So therefore, in between them, we're going to have increasing slope values as we move to the left toward the vertical slope values in this area. Anybody want to argue?
Seems good.
I see nothing to argue.
And then in the positive region, again, we're going to get more stuff like this. It's going to shrink down a bit as we get close to our slope 0 curve. Again, just mostly looking at like how intermediate value theorem plays out with all this. If you want to actually measure the values, then I highly recommend, getting some sort of like solver that can do this numerically and figure out all these individual values. TI calculators also have a, let's see, TI 86, TI 89, and 92 have the differential equation mode, which will also allow you to enter differential equations and then plot them. So you will get actually a slope field like this if you do that. You can then enter a particular initial value, and it'll give you it'll interpolate the slope field from there, or sorry, interpolate the solution that you got. I suppose it's extrapolate. Yes, extrapolate. Inspire, yeah. I mean, 89 came before the 84. Okay, so does anybody, either here or in chat, have any questions about this? Alrighty. As we have negative t values, what's going to happen?
Negative t values. You're going to have, well, a lot of positive slopes. But, let's see here. Yeah. So this minus sign is going to make the slopes. Hold on. Sorry. No, I'm just...
No, this is a hard one, so, like, maybe we shouldn't have done this first, but,
Right. But I'm trying to think it through. You have y... as t goes to infinity, you're still going to have the value y as your slope eventually, right? On the left-hand side, that's as t is really big. Never mind. I'm looking at t is going to. So if t goes to negative infinity, you're actually going to get something that goes without bounds. So you're going to get vertical lines there. Now that I'm thinking it through. So, okay. And so the exponential decay that we were experiencing before to basically y doesn't exist. We're just going to get a whole bunch of vertical lines far out to the left.
Right, and looking at the function where we had a zero slope, this is actually going to follow an even tighter path than this, but it's going to follow a path that goes down like this. It just keeps decreasing infinitely and more quickly as we go off to that side. It's partially exponential, right? So it's just going to blow up to infinity real fast.
Right.
And that's where all of the slopes are zero. But again, as you said, as we start moving at all to the negative side, beyond this, then we're going to end up with a whole bunch of positive values. So we know the slope isn't going to be zero anywhere else. We know the slope isn't going to be undefined anywhere else. So again, we're going to do like, intermediate value theorem and a couple of other tactics of reasoning to say that we're not going to get any weird, funky behavior. So having a y value of 0 and just going across the x-axis as our as we move to the left-hand side, then the first term, right, 2t e to the negative t over t, our t's are going to go away, and we're just going to get an exponentially increasing function, which is going to get us more and more positive slopes as we go further and further out. So Femvox, right, good question. How do you know the slopes don't do some other funky thing in the meantime to go from t equals 0 to very big? Basically, you could, in theory, try to find if there are any other like second derivatives to see if there are any inflection points. But for the most part, we're going to look at like where are the zero slopes, where are the infinite slopes, and there's maybe some like switching sort of behavior in here where we go from the zero slope dominating to the infinite slope dominating, right, as we get down here. But you can find out those particulars if you actually graph this for real. So if we go over to... this is the GeoGebra link that I gave you. So we'll put this in chat. Oh. Don't lose chat. You have to enter this in terms of f prime is equal to some function of x and y, but again, we have that, so that's alright. Alright, so this is going to be... where'd it go? Curses. Alright, y prime is equal to 2. I don't remember how nice this is in terms of... Oh, x. I don't remember how nice this is in terms of... Yeah, okay. We don't have to do, like, hyper-vigilant syntax. So, e to the negative t. And actually, that's going to be 2e to the negative x, because we're going to divide off the t. Sorry. I should just keep this as it is in Excalibur. Right, so 2x e to the negative x Minus t plus x plus 1 times y. Okay. There we go. Okay, so Femvox, you're right. There is going to be some other weird behavior over here. So I did not account for everything that was there. Actually, I might have. I just didn't draw in. Okay.
Yeah, that looks okay.
Right, if we increase the density, you can see more more features. Sometimes it'll actually be less if there's like a very large amount of objects, especially over here on the left, right? Sorry, just heard that. If we have a bunch of objects here on the left, almost all of these have the same slope, so it's just a field of like almost exactly the same stuff. So if we lower it a little bit, we can see sometimes. Increasing or decreasing length, again, gets us just sort of a path for our brains to follow. And if we take the initial condition and move it around, this is also going to show us how things work. So we do get some differing behavior with the asymptotes. It gets a little weird. There is some funky behavior with that stuff. And like, if we change the asymptote, how is that going to affect the final product? Okay.
And the other thing here is that question. I was just looking up something fast.
Ads jumping.
Sorry, there's an ad break.
Yep.
Again. I was doing a little research while you were talking. But I'll wait till the ad's over.
Righto, we're back. Sorry for that interruption. Femvox, awesome. See you in 10 minutes.
My understanding is that this is related to the fact that if you have a C1 function, which I think are as long as the function is C1 on our interval or on our domain, we're okay, and we won't have any shenanigans. Something called the continuous dependence. So as long as we stay away from that divide by zero line, right? Like that wall in our slope field, I think we're okay. That nothing too crazy will happen. And I think that's the guarantee that Femvox is as long as our function, our f prime is equal to something C1, then we're okay with that. Continuous and differentiable. Okay. That's what I mean by that. That's what I remembered. We had in dynamical systems, we talked about this, and so I was trying to remember the conditions there. And if I'm reading this correctly, that is how I interpret it: is as long as the function is C1 between continuous and differentiable on our rectangle, we're okay. Nothing too crazy will happen. However, when you cross the line, the t equals 0 line, that's a wall that should not be crossed.
Right. So in this particular case, it's actually not even possible to cross that line. That will end up as the function being a vertical asymptote. except not at 0. Can't do anything at 0, 0. Yep. And then here, we're going to end up with negative sloped values way in there, in that little tiny portion. Okay. And again, we can check all sorts of different stuff, but basically this is going to all have negative slopes up here. And then this is all going to also be positive on the left-hand side, quadrant 2. Okay. So we've already seen this on GeoGebra, but how do you draw solutions to differential equations by hand?
So these... Oh, go ahead. Go ahead. Sorry.
Pick a point and follow the lines.
All right. How about each of you take one?
Almost.
Cooperate. Good mouse. Over here. Over.
It's always hard to draw with a mouse.
Yeah.
All right, so how do we get these?
Each of these curves is tangent to the to each of the points that we found. It's roughly tangent. So the idea here is that you as tangent as I can get it.
Yep. Fair enough.
Right. That's sort of the idea, is that each of the line segments are tangent to the curves that we've drawn.
Yep, I will always take tangent enough.
Tangent enough, yeah.
It's
Up to
super hard to
epsilon.
draw these things.
That's all I have to say.
Yeah, it's super hard to draw these things if you haven't had the practice for it, and especially like, you know,
Right.
ever, but especially in several years. Where else might you see things like this?
Like a weather diagram, kind of looks like.
Right, because
very
each of the
chart.
individual parts, they're trying to show you what?
Like wind speed, maybe.
Yep. Yep, Don's got it,
I
right?
guess is the-
We're looking at a field of vectors. So like all of these individual tangent lines could be replaced by vectors to show us what direction and the strength of the movement is over time, especially when we're talking about time. If you're using an XY plane, for example, that's where we start getting into partial differential equations, heat diagrams, and all sorts of fun stuff like that. High and low pressure fronts. So once you start getting into partial differential equations, that's when everything starts exploding in complexity, and oftentimes there is no analytical solution. As we know, the weather can only be predicted with any remote viability for only a few days before we start getting into, we're not going to get into it, but before we start getting into the field of chaos, where even just tiny little minute differences in initial conditions can cause wild variations further on down the line. All right. Any questions?
And these are integral curves, yes? The things that we've drawn?
Yep.
Okay.
So,
I don't know if you wanted to bring that up as a word.
So integral curves are our solutions given a particular... Oh no! Ran off the edge. Initial condition. So even if you don't necessarily have an initial condition that you are explicitly trying to find, right, you always have to place it somewhere and say, like, I'm going to start from here, wherever that is. Hey, Funvox, that was real fast. So, yeah, like I said, if you don't have a particular initial condition that you are actually looking for, you can just plop down a few kind of at random and see what happens. See if there are different areas where different behaviors occur. We saw, for instance, that some of these will completely avoid that stuff way down in the quadrant 3 being real tight to the y-axis, right, where it comes back down. Any of the stuff that's over to the left far enough will eventually become asymptotic to the top rather than to the bottom. So there's all sorts of fun stuff. So watching out for changes in behavior is oftentimes a goal of people who are looking at differential equation type solutions, especially when you have slope fields and stuff like that. This is also especially useful if we don't have a nice solution. So there are going to be some differential equations where we look at them later and it's just not possible to solve it analytically. The one that we were doing here is hard enough. I mean, it is first order linear, so it's not awful. There is a solution. Yeah, but being first order linear, right, it has a solution. We know that it will. But some other ones will not, and we'll take a look at those a bit later. Any questions?
All right.
Yeah, we'll just do one more. So if you don't mind, create a slope field diagram by hand for the following differential equation. Y prime is equal to x minus y.
This one's interesting. because in a sense, as long as the x minus y is constant, then like you're gonna get like isoclines again along the line x minus y equals c, right? So everywhere at like 0, for instance, like you have slopes of 0 anytime the x and y are the same, which would be along the line x equals, right? So I would expect that, and then like if I were to have a slope or x minus y, let's see, were some other constant like -1, that would be what? It would be the line x equals y plus 1, or x minus 1 equals y. So you would get that along that line, you'd have everything that was of slope. Did I say -1? -1. I think on that line.
Yeah.
And so on and so forth. You could just continue to make diagonal lines, and the slopes will all be constant on this line.
Mm-hmm.
Feel about that.
That's
okay,
great.
so minus
That's a
1
great
is
drawing.
going to be here, right?
Let's see here. Yeah, -1. Actually, those will be positive, will they not? Because your y value is negative, but you're subtracting that. So it should be just slanted the other way. There you go.
Yep, and that's another one too, Dr. Gold. If you set one of them equal to 0 and then figure out what happens to the other one as it moves, it's another way to go. I like Zach and Stuckey's approach in this one just because like it is a constant along these particular diagonals, and that's very convenient for this one, but every time you come across one, it's going to change. So strategy changes every single time depending on what you want. Or you could just say, I'm going to set, x to be a constant in this particular thing and see what happens as we go up and down. Or set y to be a constant and figure out what's going on as we go left and right. Yep. Mm-hmm. Right, so what might your go-to be in terms of strategies? Like, i.e., how did you immediately know the isocline thing?
Well, by definition, we'd take, if we have y equals something, then the something is, you set that equal to constants, and that's where you get the isoclines from. But here we got, the good news was that the isoclines were linear, and so we've got a lot of intuition about how that looks.
Yeah, I think my immediate gut reaction was what you all had discussed on the previous one, which was immediately go for y prime is equal to 0. So, like, generally speaking, that's going to be my go-to. Yeah, and this is a first-order linear differential equation, so it's not like it's awful.
Actually, it's solvable. We can actually solve that one.
Yep. All right, let's draw in some solution curves for this one. Drawing with a mouse. Ooh.
I know, it's hard.
I did that for about 2 days during the pandemic.
We're not gonna try and draw another one.
And I was like, you know what? I have a tablet somewhere.
I need to invest in one. It's just a thing to do. But then I gotta keep the chalkboard.
Yep. Yeah,
So if it were me, I'd be putting this on the chalkboard and all that. What I ought to do actually is get out like old style projector slides. You know,
man.
do like get the old overheads. I had a professor, interestingly, who taught computer graphics in like 2009, and I took the class. He was using overhead projectors for his slides. So I have to say they were still, and I found them useful when trying to teach students about rigid motion, like high school geometry.
Yep.
I actually physically got out slides and I would move them around, showing that this is actually that sometimes the old technology is.
All depends on what you need.
The teacher I borrowed the overhead projector, though, he was very reticent to let me use it. So very much oh gosh.
All right.
Anyway.
And part C, could we find a function in X to be a solution for this particular differential equation by just observing its behaviors?
You can sort of see where it's the solution is tending to as you approach infinity, right? So you've got this line, x equals, or let's see, y equals x, that is seemingly important.
Okay. Is there another line that might be like even more important to the original function? Or original differential equation? I didn't notice the hearts.
Oh, the hearts, yeah. Didn't see those. That's cool. Maybe I'm just not seeing what you want me to see here.
That's all right. So, like, if we're trying to go for a function, you know, y of x, is there going to be a particular feature of this graph that is going to be super, super important no matter which of these solutions we have. So the one, for instance, the two solutions that we have underneath aren't going to care that much about y equals x.
Yeah, but he was talking about 5 plus x equals -1.
Okay. So if we take a look at what we have here specifically. There we go. Right, no matter what function it is, or which of these solutions it is that we're using, this line keeps cropping up. So in terms of like functional analysis, going back to pre-calc, what is this thing?
An asymptote.
That's an asymptote, yeah.
Yeah. And how would we find its equation guaranteed, regardless of what the actual differential equation was?
Well, you have to take a limit, right? That's
Potentially.
what you're getting at. The limit is as x go, or I guess as your independent variable goes to infinity. That's the thing that's going to be your solution in the long run, if that's what you're going for. But
could do that. It's going to be hard to figure it out if you don't have the solution function ahead of time. What else is guaranteed about it?
I mean, if we're requesting only slant asymptotes, then it's going to be an isocline.
I am being a huge pain in the rear here, I know.
yeah, I have no idea what you're talking about.
Okay.
Like, I'll be just blunt. I'm not seeing what you're talking about because I'm seeing an asymptotic solution.
Mm-hmm.
That seems to be the thing that stands out to me, but I know you're going for something else.
It's like if we had picked a specific initial value that was on the asymptote, because that's also a possibility. It's a thing we are allowed to do. What's going to happen?
If you're on the asymptote, your slope's going to be 0.
Is it?
Right. Well, so sorry, if you're on this line, you're going to be traveling. You're on the line, so like you're. Because you're saying like if you're on this white line, right? That's specifically. If I pick a point on that line, then we know. What is it? That's an isocline. Specifically the one where x minus y equals 1. And so y double prime. There you go. There's y double prime is 0.
Yep. So that's going to be the one in this case. If we want a solution that has a constant slope anywhere, it's probably going to have a constant slope everywhere, but then we want to have where is y double prime equal to 0. So in this particular case, we can also go back and say, okay, we have the equation y prime is equal to x minus y. So what is y double prime going to be equal to?
Right. I see what you're saying. So that's going to be what is that? With respect to x, that's 1 minus y prime.
Right, and then since we want this as an equation,
Y prime equals 1. I see what you're saying. Okay. Okay. Yeah, that's reasonable.
Right, or because we want it as an equation in y,
you could say that x minus y equals, or 1 minus x minus y equals 0.
Yeah.
I see what you're doing there. That's reasonable. Okay.
Right, so we end up with a -1 plus x is equal to y once we actually straighten this thing out. And then this is going to be our, like, most important isocline. It's going to be the asymptote.
Okay.
Now, it's not always going to work out this way. There won't always be an asymptote, but this is something to look for. Is, okay, we could see right up front that we want to know where y prime is going to be equal to 0. Megalomorph!
Well, Megalomorph, I'll just say I just haven't seen it said that way before. What about curvy asymptote? Exactly, right? Like, so that only works if you have a slant asymptote. And that's where, like, you have the degree, you have something 1 degree higher. Like, if you have a ratio of two things, one a polynomial a degree higher than another. That works, but we can't always assume that.
Yeah, that's true. It's just going to be like, can we find something that's going to make this work? So you could, in theory, have like a quadratic asymptote that you want to take a third derivative and set it equal to 0 or whatever.
Right.
You can do that stuff, but okay. So I think we're gonna move on to the second section because yeah. So this is going to be more food for thought rather than necessarily a whole lesson because we're pretty much almost at time. But, so as we start going into the next section, we want to know, for instance, if we had a particular function that is, or a particular differential equation that is not going to be particularly nice, something that you cannot solve analytically, how would we then be able to still at least get reasonable approximations for a solution? So we're going to do something ridiculously stupid and go for a differential equation dy dt is equal to t squared, because we know very obviously what the solution to this differential equation is, and then we can test how good our approximations are going to be based on a known solution and what we're going to get with our approximations. So in the case of dy dt equals t squared, we want to look at this and say, yeah. And we're going to start with y of 0 equals 3. So first off, what does the slope field for this look like?
Going to be a function of t only, right? So you've got like the only thing that in y there's going to be constant values, but there's going to be vertical lines as long as our t-axis is horizontal. We're going to have vertical lines of the same slope. So that'll be parabolic in nature. So you'll have like 0 at t where t equals 0. Did I say that? I did say that correctly. It would be vertical lines of the same slope.
Yes.
So 0 and then 1s and 4s and 9s and so on along positive integers and in the negative integers. So there'll be some even symmetry.
Right, so what's that going to look like? We'll go with do 1 and 2. We'll go like that. Approximately. Okay, so along our y-axis, we're going to have our horizontal. Give or take. And along the line, x equals 1 and x equals -1, you said?
Mm-hmm. You're going to have the you have slope of 1.
Right.
So little line segments to the slope of 1.
Right. And I'm maybe approximately doing this to scale, but you know, even if it's not 100%, I think y'all get the idea. All right, and then at 2, this is going to be 4, so we're going to go that. I started getting slower or smaller slopes as we went up, but whatever, it's close enough. Right. So if we were going to approximate a solution here for y of 0 equals 3, then just like we did before, we're going to start at 0, 3, and then say, all right, well, based on this, I know what the solution is going to look like more or less, and it's going to make this sort of curvy motion like that. More practice you get with like artistry motion, the better it gets. So actually what we were doing in the previous section and what I just did here is sort of what we're going to be doing with what Megalomorph pointed out is Euler's method. Which is to say that what we're going to do is approximate little tangent lines that we're going to draw in every so often until we get a reasonable approximation of our answer. So what we're going to do is say, okay, we're going to pick a particular delta t, and in this case, let's just have it be 0.1 for ease of doing this. That's probably a terrible idea. We can make it super chunky. And just go with 0.5. And it's going to be ridiculously low resolution. All right, so what Euler said was what we're going to do is pick our current value find the slope, draw a line segment to the next t value. You can tell how much I love cursive writing. And then we need to recalculate the slope. for the next segment. Yes, Megalomorph, we are going to talk about Rungekura next class. So that's going to be Monday. Okay, so for Euler's method, again, wherever we are on the current location, find the slope, draw a line segment to the next t-value, recalculate the slope for the next segment, draw the next one, etc. So we're just going to keep repeating this process. All right. So for this one, what are we going to get?
I'm actually gonna have to duck out
Yep, that's fine.
because it's just
Yeah,
4 o'clock.
same.
But I appreciate it.
Yep.
And thank you for putting this on.
So that'll be food for thought for next time, and we'll cut off here anyway.
Yeah.
It's just 4 o'clock, so that's why.
That's perfectly fine. That was our agreed to time anyway.
Okay.
Righto. So thank you, Stucky and Zach, for stopping in. And again, anybody else who's interested in joining the class as part of our stage crew here, please let us know in Discord, and we will... if you're known to the community, we can have you come on in and be part of the talking group here. And if not, if you want to still participate just from chat, that is perfectly fine. And we'll have anybody... Yeah, we'll have anybody on who wants to be on if you have been with us for a while. And otherwise, we'll just see you in chat. Thank you so much for coming. And I'll let Stucky and Zach go and then wrap up the last little bit.
Thank you.
So much for hosting.
Yep, thank you. And here are Stucky and Zach's information, Discord, and their Twitch pages as well. So if you have any interest in doing that, there they are. I think what's going to happen is I'm going to just wrap this up and then do a 3-minute ad, and then I'm still feeling pretty good, so we'll just play a game for the rest of the night. Wonder why that is. Yeah, anyway. So, thanks everybody for coming. If you're going to stick around, again, I'll just run a 3-minute ad, and then we'll be good for another hour. What we're going to be doing for the rest of the week is... Thank you so much for lurking, Zach. We're going to be taking a day off tomorrow, getting a few of the VODs uploaded and clipped into highlights, and I'll make sure to put a bin in for Differential Equations class, so you can go back and check all of those out in one central repository. I actually need to do that. Haven't done it in a while. On Friday, we'll be playing a game, most likely either Breath of the Wild or going back to Elite Dangerous, depending on if there's a war on still or not. Our community is trying to get consolidation going on there. On Monday, like I said, we'll be doing numerical analysis for numerical solutions of differential equations, how we get to all of the individual different numerical solution types. We're going to be talking about Euler's method, which we highlighted here. If you want to go ahead and try to get Euler's method, like try to suss it out by itself, let me know. And I'll still drop some homework in our Discord server. But I won't include Euler's method except as like a challenge problem or something. We'll also be talking about the backward Euler method, which is objectively awful, I think, just for me, but it's kind of interesting. And then we'll be talking about Rungekura, and there's one other that I keep forgetting. I think it's modified Euler. It's the Hoyne method. Anyway, and we're going to talk about how all of these things relate back to Calc 2, because most of them have sort of an analog of integral solutions that you all found from Calc 2. It's really cool stuff, and I hope you all check in. We're going to be doing that on Monday, and on Wednesday we're going to actually get into our... I think that's where we start getting into our second unit stuff, so that's exciting. We'll also talk a little bit about how to do some of this stuff in MATLAB if I can get Octave to work, cooperate properly. And might be able to figure out some other applications that we'll be able to use. I think really Octave/MATLAB is the one that I'm most familiar with, so that's the one I use. But pretty much anything you want to do, you can do it easily enough in Python or another programming language, as long as you have some basic math. It's very easy to figure out. Okay, so I'm going to grab some more water, cycle, and then be back in 3 minutes. Hope you all come back for mathy type stuff on next Monday and Wednesday for differential equations. Hope you all are checking out Penn Center's complex analysis class on Tuesdays and Thursdays. And Zach is going to be running an infinite series class in September, so that's something to plan for if you're at all interested. It'll be at the very least something very interesting to watch. So I will be back in approximately 3 minutes, and thank you very much for sticking around. Those of you who will stick around, we'll be back shortly. Thanks so much. The demonic power of differential equations is coursing through my veins, yes. And a crap ton of coffee. It's only 11 o'clock, it's fine. Alright, we will, provided that Baldur's Gate is actually going to launch, we will be doing Baldur's Gate 3. It says running. That's good. Open settings. Steam Tinker launch. Vortex. Come on. Come on. Come on. Almost there. Uh-oh. Uh-oh. Is that not... Uh-oh. Play. Nope, not that. Different settings. Oh no. It might not work. Download custom Proton. Oh, Proton 910. Okay. Is Zach going to be running an infinite series of lectures on infinite series? You know, that I don't know, but we can always run recursion by unmuting myself in the stream, so that could be interesting. But we can always run recursion by unmuting myself in the stream, so that could be interesting. But we can always... It's fine. All right. Oh no. Please tell me I didn't just break it. Already. Oh, there we go. Compatibility. Steam Tinker launch. Cool. Okay, so that setting's correct. Game menu. There we go. Proton. 910. Save and play. Let's go. Using Proton 910. Looking good. Looking good. Come on, come on, come on, come on, come on. You know, I had a similar problem with a bunch of our Next Fest demos. They just would not work. I was like, great. This is working. Alright, here we go. Alright, DirectX 11, I believe, is the correct one. It's been a while since I've actually played this, but, you know. Yay, here we go. Okay, so let's switch windows now that it's actually working.